Welcome back to the channel. This video is on geology and the Earth's interior, and this video is looking at the difference between the chemical layers and the physical layers of the Earth's interior. This is the Earth Science Classroom. Planet Earth is the largest of the 4 terrestrial planets that are revolving around the Sun. Now the others are Mercury, Venus, Mars, and obviously Earth. Earth is the largest with around 25,000 miles circumference and around an 8,000 mile diameter or 4,000 mile radius. Now why is this important? Well, because it is a large planet made of rock. That's what terrestrial means, layers of rock. Now, how do we figure out what the Earth's interior looks like, is composed of, its densities and different characteristics, and also the temperature? Now, all this information, all this knowledge of our Earth's interior have come from one scientific discipline called seismology, which is the study of seismic waves, which are produced by earthquakes, which then propagate and move throughout the entire Earth's interior through different layers, and the analysis and studying of these waves have allowed scientists to decode and understand the Earth's interior through different seismic wave velocities. So what happens is, during different states of matter, densities from high density material to low density material into semi-solid or even liquid material, these waves would change speed, they change their velocity based on the ability to move and pass along the energy required to move this seismic wave from point A to point B. So in a dense material, it becomes easier to transfer the energy, therefore the wave or the elastic energy moves quicker with higher velocities. In a semi-solid or liquid material or medium, the energy is not passed on as quickly, therefore the wave would slow down and velocities would decrease. So if you look at this on a seismograph, a machine that records the shaking due to an earthquake and the waves, you can see that there are changes in velocities of that wave, and you can work backwards from there and then interpret these changes of velocity to the changing densities of the Earth's interior. And this was calculated back in 1909 by a scientist called Mohovic in a country called Croatia, or back then it wasn't Croatia, but nowadays it's Croatia in Europe. Our planet's interior is separated or divided into 2 different types of layers. One is the chemical layer and 2 is the physical layers. Now, the chemical layers refer to the chemistry, the elements, the atoms that are inside the Earth's interior. And what they found was that the chemistry of the Earth is in 3 distinct layers. 1 is the core, 2 is the mantle, and 3 is the crust, compared to the physical layers, which refers to the density, the temperature, and the physical state of matter of each of the layers. They found that it splits into 6 distinct layers. So for physical, 1 is the inner core, 2 is the outer core, 3 is the mesosphere or mesosphere, which is the lower mantle, 4, which is the asthenosphere, 5, which is the lithosphere, litho means rock in ancient Greek, and 6 is the crust. So you've got 2 types of layers, the chemical and the physical. We're going to start off with the chemical layers. The first, which is the core, the inside the Earth. Its composition, its chemistry is mostly 85% iron and about 15% nickel. These are metallic elements. Our next chemical layer is the mantle, number 2. Its composition is generally ultramafic and mafic rocks. The final chemical layer is the very thin crust. Its composition is mostly lighter, less dense silicate minerals forming various basaltic and granitic igneous rocks. Now we move into the physical layers, which is the other characteristics of the layers found through the analysis of these elastic energy, these seismic waves from the earthquakes. And the inner core, the center of the planet, has a density of around 364 gigapascals, or equivalent to about 51 million psi, which is pounds per square inch, which is absolutely insane. And it is a solid material, and its temperature ranges between 5,500 to 6,500 degrees Celsius. In regards to the physical layers, the core is split into two divisions, the inner core, as mentioned earlier, and this one is the outer core. So this is a little less pressure, a little less density, so it's still incredibly dense and under a lot of pressure. However, it's less than the inner core. It's looking at about 136 to 360 gigapascals of density. That's equivalent to about 19.5 to 50 million psi. Now, I put a range because of the thickness. So the lesser density would be towards the outside of the outer core, away from the center, and towards the middle of the Earth, towards the middle or the center of the outer core, looking at the higher values of density. And the same thing with temperature. So 4,500 to about 5,500, and the state of matter is liquid because of the temperature outweighs or surpasses the pressure, therefore allowing it to melt this part of the Earth's interior. Now, this also refers to the Gutenberg discontinuity, which is the boundary between the outer core and the next layer, the mesosphere, and also the Bullen discontinuity, which is the boundary between the outer core and the inner core. And these boundaries, these discontinuities, refer to a sharp change in velocity of the observed seismic waves, marking a change, a very abrupt change between the different mediums, the physical characteristics of these layers. The third physical layer is the mesosphere or mesosphere. Meso in Latin or Greek means middle, and this means the lower mantle. So it's a large chunk of the mantle, and this density ranges from 24.5 gigapascals up to 136 gigapascals, or equivalent to 3.5 million to about 19.5 million psi. Again, still insanely dense with a lot of pressure. The temperature reflects that, 1,500 to about 3,700 degrees Celsius, and the state of matter, the layer is solid. Now we've entered the upper mantle, the asthenosphere, which astheno means weak or less solid in Greek, and the density is between 3 gigapascals to 24.5 gigapascals, or equivalent to about 400,000 psi to 3.5 million psi, again, based on the range and the depth and the thickness of where you take the density and the pressure. And this state of matter is solid, mostly solid, but there is a semi-solid and small part of low velocity zone, which means that the state of matter is semi-solid, even part liquid, because of the slowing down or decreasing in seismic wave velocity through this low velocity zone, which occurs around 100 to 150 kilometers into the asthenosphere below the lithosphere, which denotes an area of magma formation. Now, the temperature is between 900 to about 1,400 degrees Celsius. We're still in the upper mantle. This is the lithosphere. Litho means rock or rocky layer in ancient Greek. Density is, again, from the surface to about 3 gigapascals, surface being 0, or around max of 400,000 psi. Now, why is this at the surface when it's not the top layer, number 6? Is because the lithosphere includes the 6th layer, which is the crust. And the lithosphere is that top layer that is part of the upper mantle, but also contains the crust, which is that surface layer. So the temperature ranges from, again, 0 to about 900 degrees Celsius. And this refers to what's called the geotherm, which is the increase or rate of change of temperature as you increase depth going down into the Earth's interior. So with every increase in depth of 100, 200 miles or kilometers, you'll see an increase in temperature based on the pressure, the bulk modulus, and the mass of the rock above it with the force of gravity, all combining to create a certain temperature and pressure at a certain depth. And this pressure is denoted as what's called lithostatic pressure, which means the pressure is coming from all areas onto that material. As mentioned before, the crust is a part of the lithosphere, but the crust is separated into two types. You have continental and oceanic. This is based on what terrain or what environment is on top of that particular part of the crust. If the surface is ocean, then the ocean floor, that is part of the oceanic crust, which is generally thinner. The continental crust above the ocean surface at sea level, the continents, the land masses, the islands, that is generally a thicker section of the lithosphere that we call the continental crust. So it's all part of the lithosphere. However, there is a difference in the physical characteristics, so therefore they separate the crust, the two types, and the lithosphere. However, in reality, they are just together, and the MOHO is the discontinuity that was found in 1909 by the seismologist Mohovich. So MOHO is the shortened version of Mohovich, and this line, this certain depth, denotes the change from the crust into the mantle, which is the asthenosphere, the upper mantle. That sharp increase in velocity because the density increases. Now, the density of the crust, the oceanic crust, is around 3.0 grams per centimeter cubed. It's a little bit heavier and denser than the continents at 2.7. And this is a solid rock layer that also is brittle, which comes into play when discussing crustal deformation, continental drift, seafloor spreading, and also plate tectonics. The temperature ranges again as the lithosphere between 0 to 900 degrees Celsius. Again, with the geotherm, and increase in depth comes increase in temperature. So there is a range between the depth, the lowest part of the continental crust, which could be as deep as 100 kilometers or 70 miles, or a shallower oceanic crust, which could be only about 15 kilometers thick or about 9 to 10 miles thick. When you combine both the chemical and physical characteristics of the Earth's interior layers, we get a better understanding of how this planet functions, and the result of the Earth's interior is shown on the surface through crustal deformation, earthquakes, tectonics, tsunamis, mountain building orogeny, and still this information has been acquired through the proxy indicators, the estimated analysis of just seismic waves and how these waves are propagating or moving through the Earth's interior at different velocities. This is the Earth Science Classroom. Thanks for watching the video. If you liked it, please subscribe, like, and share. And if you want more content and videos on Earth science, please check out my channel.